On December 14, 1972, a man named Eugene Cernan climbed a small metal ladder on the side of a spacecraft and stepped onto the surface of the moon for the last time. He was not the first person to walk on the moon. That honor belonged to Neil Armstrong, 3 years and 5 months earlier, on a July night that the entire world watched in silence. Cernan was not even the second or the third. By the time he arrived, 11 other men had already left their boot prints in the lunar dust. But Cernan would be the last. And somehow, standing on the surface of another world for the final time, he seemed to know it. Before he climbed back into the lunar module, Cernan knelt in the regolith and used his finger to trace his daughter's initials into the dust. T.D.C. Tracy Dawn Cernan. She was 9 years old. She would never visit the moon herself. No one would. Not for a very, very long time. Cernan spoke a few words into his radio, his voice steady but tinged with something that sounded like reluctance. He said that he was leaving the surface, and that America's challenge of today had forged man's destiny of tomorrow. Then he climbed the ladder, sealed the hatch, and lifted off. If you enjoy this kind of calm, unhurried journey through the biggest stories in science and space, you might want to subscribe to the channel. We release new episodes every single night, designed to be the last thing you hear before you fall asleep. A tap of that subscribe button means you will never miss one, and it means the world to us. Now, let us continue. The ascent stage of the lunar module fired its engine and rose from the surface in a plume of silent flame. There is no sound on the moon, no atmosphere to carry the roar of a rocket engine. The departure was visually dramatic, but acoustically empty, a column of fire rising against a black sky in perfect, absolute silence. The lunar module rendezvoused with the command module in orbit. The crew transferred over, and the empty ascent stage was jettisoned. It fell back to the moon, crashing somewhere on the surface with an impact that the seismometers left behind by earlier missions recorded as a small, brief tremor. Then the command module fired its engine one last time, broke free of lunar orbit, and began the 3-day journey home. Apollo 17 splashed down in the Pacific Ocean on December 19, 1972. The crew was recovered. The spacecraft was secured. The mission was declared a complete success. And then, quietly, without ceremony, without any formal announcement, the Apollo program ended. The remaining missions, Apollo 18, 19, and 20, had already been canceled. The Saturn V rockets that would have carried them were sent to museums. The lunar module production lines were shut down. The army of engineers, technicians, scientists, and flight controllers who had made the moon landings possible were reassigned or let go. Within a few years, the infrastructure that had taken the better part of a decade to build was dismantled, repurposed, or simply abandoned. But before we talk about why it ended, it is worth pausing to appreciate what each of those missions actually accomplished, because each one was unique, and each one pushed the boundaries of what was possible a little further than the one before. Apollo 11, in July of 1969, was the proof of concept. Armstrong and Aldrin spent just 2 hours and 31 minutes walking on the surface in the Sea of Tranquility. They planted a flag, set up a small package of scientific instruments, collected about 48 pounds of lunar samples, and came home. The science was secondary to the achievement itself. The entire world was watching, an estimated 600 million people, the largest television audience in history at that time. In living rooms and town squares, in hospitals and schools, in places that had never seen a television before. People gathered around flickering screens and watched a grainy, ghostly figure step off a ladder and onto the surface of another world. The moment transcended politics, language, and geography. For a few hours, the entire human species shared a single experience. Apollo 12, just 4 months later, in November of 1969, demonstrated precision. The crew landed within walking distance of the Surveyor 3 probe, an unmanned spacecraft that had landed on the Moon 2.5 years earlier. The astronauts walked over to the old probe, removed its camera, and brought it home. This was not just a stunt. It proved that NASA could land exactly where it wanted to on the lunar surface, a capability that would be essential for future missions that needed to reach specific geological targets. Apollo 12 also deployed the first full Apollo lunar surface experiments package, a suite of instruments powered by a small nuclear generator that would continue transmitting data back to Earth for years after the astronauts departed. Apollo 13, in April of 1970, never landed. An oxygen tank in the service module exploded roughly 56 hours into the mission, crippling the spacecraft and forcing the crew to use the lunar module as a lifeboat. The mission became a survival story, a desperate improvisation by the crew and the flight controllers in Houston to bring 3 men home alive through a crippled vehicle with failing systems. They succeeded, barely, and Apollo 13 became the most famous space mission that never reached its destination. But the near disaster had a chilling effect on public enthusiasm. The very danger that made the mission gripping also raised uncomfortable questions about whether the risks were justified. Apollo 14, in February of 1971, saw Alan Shepard, the first American in space and now the oldest person to walk on the Moon at age 47, strike 2 golf balls across the lunar surface with a makeshift club fashioned from a sample collection tool. The mission explored the Fra Mauro Formation, the original target of Apollo 13, and brought back about 94 pounds of samples that included some of the oldest rocks found during the Apollo program, dating back more than 4 billion years. These ancient samples helped scientists understand the violent early history of the solar system, a period called the Late Heavy Bombardment, when the inner planets were pummeled by asteroids and comets. Apollo 15, in July of 1971, was the first of the extended missions, the so-called J missions, which carried a lunar roving vehicle that allowed the astronauts to travel much farther from the landing site than on foot. The crew explored the Hadley Rhyl, a winding channel carved by ancient lava flows at the base of the Apennine Mountains, one of the most dramatic landscapes on the Moon. They found the so-called Genesis Rock, a sample of an orthosite that was later dated to 4.1 billion years old, one of the oldest intact pieces of the original lunar crust ever recovered. This single rock told scientists more about the Moon's formation than years of telescope observations had managed. Apollo 16, in April of 1972, explored the Descartes Highlands, the first mission to land in the lunar highlands rather than the relatively flat Maria. The crew discovered, to the surprise of many geologists, that the highlands were not volcanic as had been expected, but were instead composed of impact breccias, rocks shattered and reformed by billions of years of meteorite impacts. This finding reshaped the scientific understanding of the Moon's geological history and emphasized how much remained unknown even after multiple landing missions. And Apollo 17, the final mission, was in many ways the most scientifically productive of all. It was the only mission to carry a professional geologist, Harrison Schmitt, who had trained as a pilot specifically for the chance to walk on the moon. Schmitt and Cernan spent more than 22 hours outside the lunar module over 3 separate excursions, covering more distance and collecting more samples than any previous crew. Schmitt discovered orange soil near Shorty Crater, a deposit of tiny volcanic glass beads that had been erupted from deep within the moon billions of years ago, providing evidence that the moon's interior had once been far more active than anyone had realized. Together, the 6 Apollo landings collected 842 pounds of lunar samples, deployed dozens of scientific instruments, and provided a wealth of data that scientists are still studying today. And yet, the total area explored was astonishingly small. If you add up all the ground covered by every astronaut on every mission, including the extended traverses made possible by the lunar rover, the total comes to roughly 60 square miles. The moon's surface area is about 14.6 million square miles. Apollo explored less than 1/1,000,000th of it. So why did the public lose interest so quickly? How is it possible that landing on the moon, arguably the greatest technical achievement in human history, became boring within the span of a few years? The answer lies in the peculiar relationship between novelty and attention. The first moon landing was unprecedented. Nothing like it had ever happened before. Every aspect of it was new, dramatic, and fraught with danger. But the second landing, while equally dangerous and technically demanding, was not unprecedented. It was a repetition. And by the third and fourth landings, the sense of routine had settled in. Television networks found that their audiences shrank with each successive mission. The ratings for Apollo 12 were a fraction of those for Apollo 11. By the time Apollo 14 launched, some networks had stopped providing continuous live coverage. This was not because the missions were unimportant. Each one pushed further, stayed longer, and discovered more than the one before. But the public, and the politicians who responded to public opinion, operated on a different timescale than scientists. For the public, the question had been answered. Can we go to the moon? Yes, we can. And once that question was answered, the follow-up, what can we learn there, was less compelling. It lacked the narrative drama of a race, the urgency of competition, the clear and simple goal that had driven the program from the beginning. There was also the matter of cost. The Apollo program, from its inception in 1961 to its conclusion in 1972, cost approximately $25.4 billion in the currency of that era. Adjusted for inflation, that figure translates to roughly $260 billion in today's money. A single Apollo mission cost the equivalent of roughly 25 to 30 billion modern dollars, when you account for the proportional share of development costs, manufacturing, operations, and recovery. To put that in perspective, the entire annual budget of NASA today is about $25 billion. In the late 1960s, at the peak of the Apollo program, NASA consumed roughly 4.4% of the entire federal budget. By comparison, it currently receives less than half of 1%. The American public in the early 1970s was not prepared to continue spending that kind of money on something that had already been accomplished, especially when the country was simultaneously fighting an expensive and deeply unpopular war in Vietnam, and grappling with pressing domestic issues including poverty, civil rights, and a struggling economy. The political motivation that had driven the space race was fading. The Soviet Union, whose early lead in space had prompted President Kennedy to commit the nation to reaching the moon before the end of the 1960s, had quietly abandoned its own crewed lunar program after a series of catastrophic failures with its N-1 rocket. With the competition gone, the urgency disappeared. The Vietnam War was consuming enormous amounts of money and political attention. The American public, which had watched the first moon landing with breathless wonder, had grown accustomed to lunar missions with startling speed. By the time Apollo 13 suffered its near-fatal accident in April of 1970, some television networks had not even bothered to broadcast the crew's routine transmissions from space. It took a life-threatening emergency to make the moon interesting again, and even that interest faded quickly once the crew was safely home. There was also a deeper issue, one that went beyond politics and budgets. Apollo had achieved its primary objective. It had landed Americans on the moon before the end of the decade, just as Kennedy had promised. But it had not established any lasting presence. Each mission was a visit, not a settlement. The astronauts arrived, spent a few days, collected some rocks, planted a flag, and left. There was no infrastructure, no habitat, no supply chain, no reason to go back that justified the extraordinary cost. And what it produced, in the cold calculus of political accounting, was a collection of lunar samples, a handful of scientific instruments left on the surface, and the intangible but powerful achievement of having proven that it could be done. For many policymakers, that was enough. The moon had been conquered. It was time to move on, and so humanity moved on. The Space Shuttle program was developed, designed to provide routine access to low Earth orbit rather than deep space. The International Space Station was built, a remarkable feat of international cooperation, but one that orbited only about 400 kilometers above the Earth's surface, a distance you could drive in a few hours on a highway. The Hubble Space Telescope was launched, revealing the universe in breathtaking detail. Robotic probes were sent to Mars, Jupiter, Saturn, and beyond. But no human being traveled farther than low Earth orbit. Not in the 1980s, not in the 1990s, not in the 2000s, not in the 2010s. For more than half a century, the farthest point any human had reached remained the same: 248,655 miles from Earth, the distance of the far side of the moon, achieved by the crew of Apollo 13 during their emergency free return trajectory in April of 1970. That record stood untouched for 53 years, through the administrations of 11 different presidents, through the rise of personal computers and the internet and smartphones and electric cars and artificial intelligence. Humanity split the atom, sequenced its own genome, connected billions of people through a global digital network, and landed robots on Mars. But it did not go back to the moon. The last footprint Eugene Cernan left in the lunar dust remained undisturbed, preserved in the vacuum for decades, as if the moon itself were waiting. And then, on April 1st, 2026, something changed. At 9:17 in the morning, Eastern Daylight Time, a rocket unlike any that had flown before lifted off from Launch Complex 39B at the Kennedy Space Center in Florida. It was the Space Launch System, the most powerful rocket ever built by NASA, standing 322 feet tall, weighing 6 million pounds fully fueled, and producing 8.8 million pounds of thrust at liftoff. Strapped to its top was the Orion spacecraft, a capsule designed from the ground up for one purpose: to carry human beings beyond low Earth orbit and bring them safely home. And inside that capsule, strapped into their seats, hearts pounding, hands steady on the controls, were 4 astronauts. Commander Reid Wiseman, a Navy testee, pilot and veteran of a previous mission to the International Space Station. Pilot Victor Glover, another Navy aviator who had served as pilot on the first operational flight of the SpaceX Crew Dragon. Mission Specialist Christina Koch, a physicist and electrical engineer who held the record for the longest single spaceflight by a woman, having spent 328 consecutive days aboard the International Space Station. And Mission Specialist Jeremy Hansen, a fighter pilot and the first Canadian to fly on a lunar mission, representing the Canadian Space Agency's contribution to the Artemis program. These 4 people were about to do something that no human being had done in more than half a century. They were going to leave Earth orbit. They were going to fly to the moon. They were going to swing around the far side, losing all contact with Earth for roughly 40 minutes as they passed through the communications shadow. And they were going to come home, re-entering Earth's atmosphere at 25,000 miles per hour, the fastest any crewed vehicle had traveled since Apollo 17 made the same journey in December of 1972. This was Artemis II, the first crewed mission of the Artemis program, the first time human beings had ventured beyond low Earth orbit since the end of Apollo, the first step in a plan that NASA hoped would lead, within a few years, to the first woman and the first person of color walking on the lunar surface, and the first real test of whether the hardware, the planning, and the people were ready for the challenges of deep space. But to understand why this mission happened, why it took 53 years for humanity to return, and why the stakes were so extraordinarily high, we need to go back. Not just to Apollo, but to the long, complicated, often frustrating story of how the Artemis program came to be. Because Artemis did not emerge from a single bold decision. It was not born in a single speech or a single moment of national determination. It was assembled piece by piece over decades through canceled programs and redesigned hardware and shifting political winds, through failures and setbacks and compromises that stretched the patience of everyone involved. And it almost did not happen at all. Section 2. The Long Road Back. The idea of returning to the moon never truly died. Even during the darkest years of the post-Apollo era, when human spaceflight seemed stuck in low Earth orbit with no clear path forward, there were always people within NASA, within the aerospace industry, and within the scientific community who believed that the moon was not finished. They argued that Apollo had barely scratched the surface, both literally and figuratively. The 6 landing missions had explored a total area smaller than a single neighborhood in a medium-sized city. They had spent a combined total of roughly 12.5 days on the lunar surface, across all 6 landings. They had collected about 842 pounds of lunar samples, brought them back to Earth, and locked most of them away in vaults in Houston, where many remain to this day. What Apollo had revealed was tantalizing but incomplete. A world of unexpected complexity, with a violent geological history, a mysterious interior, and resources that no one in the 1960s had anticipated. The most significant of those resources was water. For decades after Apollo, the prevailing view was that the moon was bone dry. The lunar samples brought back by the astronauts contained no significant traces of water. The surface was baked by unfiltered solar radiation during the long lunar day, which lasts about 2 weeks, and frozen to temperatures far below anything found naturally on Earth during the equally long lunar night. There seemed to be no mechanism by which water could survive on such a world. But beginning in the late 1990s, a series of robotic missions began to challenge that assumption. In 1998, NASA's Lunar Prospector spacecraft detected elevated levels of hydrogen at the lunar poles, suggesting the possible presence of water ice in permanently shadowed craters, regions near the poles that have not seen sunlight in billions of years. In 2009, NASA's LCROSS mission deliberately crashed a rocket stage into a permanently shadowed crater near the lunar south pole and observed the resulting plume with instruments aboard a trailing spacecraft. The data confirmed the presence of water ice, along with other volatile compounds including methane, ammonia, and carbon dioxide. This changed everything. Water on the moon was not just scientifically interesting, it was strategically transformative. Water can be split into hydrogen and oxygen through electrolysis. Hydrogen and oxygen, when recombined, are among the most powerful chemical rocket propellants known. A permanent source of water on the moon meant, in principle, that the moon could serve as a refueling station for missions deeper into the solar system. Spacecraft could launch from Earth with only enough fuel to reach the moon, refuel there using locally produced propellant, and then continue on to Mars or beyond. This would dramatically reduce the amount of mass that needed to be launched from Earth's surface, the most expensive and energy-intensive part of any space mission. The moon, in this vision, was not a destination. It was a stepping stone, a gateway to the rest of the solar system. The idea of using the moon as a waypoint was not new. It had been proposed as early as the 1950s by Wernher von Braun and other space visionaries. But without confirmed water resources, it had remained theoretical. With water confirmed, it became a practical possibility, at least in principle. And it gave the advocates of a lunar return a powerful argument that had nothing to do with nostalgia or prestige. Going back to the moon was not about repeating what Apollo had done. It was about doing something Apollo had never attempted, establishing a sustained, permanent human presence on another world. But turning that vision into reality required political will, sustained funding, and a level of institutional commitment that proved extraordinarily difficult to achieve. The history of NASA's attempts to develop a post-shuttle, beyond low Earth orbit human spaceflight program is a story of repeated starts and stops, of programs announced with great fanfare and then quietly canceled or restructured when administrations changed or budgets shifted. In 2004, President George W. Bush announced the vision for space exploration, calling for a return to the moon by 2020 using a new spacecraft and rocket system. This led to the Constellation program, which began developing the Ares rockets and the Orion crew vehicle. The Constellation program was ambitious in its scope. It envisioned two new rockets, the Ares I, a smaller vehicle designed to launch the Orion crew capsule into Earth orbit, and the Ares V, a massive heavy-lift rocket that would carry the lunar lander and other cargo. The two vehicles would launch separately, rendezvous in Earth orbit, and then proceed together to the moon. It was a complex architecture, and it ran into serious problems almost immediately. The Ares I rocket, in particular, suffered from a vexing engineering challenge known as thrust oscillation. The first stage of Ares I was a single 5-segment solid rocket booster, derived from the Space Shuttle's 4-segment boosters, but with an additional segment for more thrust. During testing, engineers discovered that this longer booster produced dangerous vibrations at certain frequencies as it burned through its propellant. The oscillations were rhythmic, pulsing pressure waves that traveled up through the rocket's structure at frequencies that happened to match the natural resonance of the vehicle. This meant the vibrations amplified rather than dampened, growing stronger as they bounced back and forth through the structure. At their worst, these vibrations could have shaken the crew with forces that exceeded the human tolerance threshold, potentially causing injury or incapacitating the astronauts during the most critical phase of ascent. NASA engineers spent years and hundreds of millions of dollars developing dampening systems to counteract the problem, including a complex shock absorber mechanism mounted between the first stage and the upper stage. But the problem was never fully solved to everyone's satisfaction, and it became one of the technical albatrosses hanging around the Constellation program's neck. The cost overruns were staggering. An independent review committee, known as the Augustine Committee after its chairman, former Lockheed Martin CEO Norman Augustine, was convened in 2009 to assess the state of NASA's human spaceflight program. The committee's findings were bleak. Constellation was significantly over budget and behind schedule. At its current funding level, the committee concluded, NASA would not return humans to the Moon until the late 2020s at the earliest, nearly a decade behind the original target. The program was consuming so much of NASA's budget that other critical programs, including the International Space Station, were being starved of resources. The committee recommended several alternative architectures, but the underlying message was clear. Constellation, as designed, was not financially sustainable. In 2010, President Obama canceled Constellation, keeping only the Orion capsule and redirecting NASA toward a different vision. Instead of returning to the Moon, Obama proposed what became known as the Asteroid Redirect Mission, or ARM. The concept was audacious but politically convenient. A robotic spacecraft would travel to a near-Earth asteroid, capture either a small asteroid or a boulder from a larger one, and redirect it into a stable orbit around the Moon. Astronauts aboard Orion would then travel to this captured asteroid in lunar orbit and study it, practicing the deep space operations that would eventually be needed for a mission to Mars. Obama explicitly stated that the Moon was not the goal, declaring in a speech at the Kennedy Space Center that, quote, "We have been there before," end quote, and that the new frontier lay at asteroids, and ultimately, Mars. The asteroid redirect mission was controversial from the start. Many in the scientific community questioned its value. The engineering challenges of capturing and redirecting an asteroid were immense and largely unprecedented. The mission's connection to the eventual goal of Mars exploration was tenuous at best. Members of Congress from states with significant NASA contractor presence pushed back fiercely, arguing that canceling Constellation would destroy thousands of skilled jobs. And perhaps most damagingly, the ARM lacked the kind of simple, compelling narrative that had made Apollo so powerful. Go to the Moon was a goal anyone could understand. Capture a piece of an asteroid and put it near the Moon so astronauts can visit it was not. The ARM never generated significant public enthusiasm, and it was formally canceled in 2017 when the Trump administration took office and redirected NASA back toward the Moon. In 2017, the Trump administration issued Space Policy Directive 1, which directed NASA to lead an innovative and sustainable program of exploration with commercial and international partners to enable human expansion across the solar system, beginning with the Moon. This directive gave birth to the Artemis program, named after the twin sister of Apollo in Greek mythology. Artemis was to be different from Apollo in several important ways. It would be international, incorporating contributions from the European Space Agency, the Canadian Space Agency, the Japan Aerospace Exploration Agency, and others. It would rely heavily on commercial partners, with companies like SpaceX and Blue Origin competing to build lunar landers and other hardware. And it would prioritize sustainability over flags and footprints missions, aiming to establish a long-term presence at the lunar South Pole where water ice had been detected. The international dimension of Artemis was not merely symbolic. The European Space Agency made one of the most critical contributions to the entire program by building the European Service Module for the Orion spacecraft. The story of how this came about is a fascinating example of international space cooperation. When NASA was designing Orion under the Constellation program, the agency realized it needed a service module, the unpiloted section that provides propulsion, power, and life support consumables. Building one from scratch would be expensive and time-consuming. The European Space Agency, eager to participate in deep space human exploration but lacking the budget to develop its own crewed spacecraft, proposed a deal. ESA would design and build the service module, based on the technology it had developed for the automated transfer vehicle, a cargo spacecraft that had successfully resupplied the International Space Station. In return, ESA would earn a seat at the table of lunar exploration and offset some of its International Space Station operational costs. NASA agreed, and the arrangement became one of the most significant transatlantic space partnerships since the space station itself. Airbus Defence and Space, headquartered in Bremen, Germany, became the prime contractor, assembling the service module from components manufactured across 10 European countries. The service module's main engine, the Orbital Maneuvering System engine, was itself a piece of American heritage, adapted from engines originally built for the Space Shuttle, but now integrated into a European-built vehicle that would push an American capsule to the Moon. Canada's contribution was equally significant in its own way. The Canadian Space Agency committed to building Canadarm3, a next-generation robotic arm system for the Gateway Station, the small orbital outpost that Artemis would eventually place in lunar orbit. Canada's expertise in space robotics stretches back to the original Canadarm on the Space Shuttle and the Canadarm2 on the International Space Station, which has been grappling visiting spacecraft and assisting astronauts with maintenance tasks since 2001. Canadarm3 would be even more advanced, designed to operate autonomously without direct human control, capable of maintaining the Gateway Station during the long periods when no crew would be aboard. In exchange for this contribution, Canada received a guarantee that the Canadian astronauts would fly on Artemis missions, which is how Jeremy Hansen earned his seat aboard Artemis II. Japan's JAXA agreed to provide components for the Gateway's habitation module, as well as a pressurized lunar rover for surface missions. The rover would allow astronauts to travel across the lunar surface in a shirt-sleeve environment, dramatically extending the range of exploration beyond what would be possible on foot in a spacesuit. The commercial partnerships were equally transformative and far more contentious. In April of 2021, NASA announced that it had selected SpaceX's Starship as the human landing system for Artemis III, the first mission that would actually put boots on the lunar surface. The decision was stunning, both for who was chosen and for who was not. Blue Origin, led by Amazon founder Jeff Bezos, had proposed a more conventional lander design developed by a team that included Lockheed Martin, Northrop Grumman, and Draper. Dynetics, a defense contractor, had proposed an innovative low-slung lander design, but NASA selected SpaceX alone, awarding a contract worth roughly $2.9 billion. Blue Origin, filed a formal protest with the Government Accountability Office, and when that was rejected, sued NASA in the Federal Court of Claims. The lawsuit delayed the program by months before it was eventually dismissed. The controversy over the Starship selection ran deeper than contractual disputes. SpaceX's Starship was an unconventional choice for a lunar lander. It was enormous, standing roughly 160 feet tall in its lunar lander configuration, far larger than any lunar lander ever proposed. It would need to be refueled in Earth orbit before it could proceed to the Moon, requiring multiple tanker launches and an orbital refueling operation that had never been demonstrated at that scale. Critics argued that the approach was too risky, too dependent on unproven technologies, and too reliant on a single commercial provider. Supporters countered that Starship's vast cargo capacity would allow it to carry far more equipment and supplies to the lunar surface than any competing design, and that SpaceX's track record with the Falcon 9 and Crew Dragon demonstrated the company's ability to deliver on ambitious development programs. The debate continued, even as SpaceX pressed forward with development and testing. The centerpiece of the Artemis architecture was the Space Launch System, or SLS, a heavy-lift rocket that had been in development since 2011. SLS was derived in part from space shuttle technology, using modified shuttle main engines and solid rocket boosters to generate the enormous thrust needed to send the Orion capsule on a trajectory to the Moon. The Orion capsule itself, which had survived the cancellation of Constellation, was built by Lockheed Martin and was significantly larger and more capable than the Apollo command module. It could support a crew of 4 for up to 21 days in deep space, compared to Apollo's maximum of about 12 days for a crew of 3. But developing SLS and Orion took far longer and cost far more than originally planned. SLS consumed roughly $23 billion in development costs before its first flight. Orion added another roughly $20 billion. The program was criticized for being too expensive, too slow, and too reliant on legacy hardware and contracting methods. Critics pointed out that commercial rockets like SpaceX's Falcon Heavy and the under-development Starship could potentially achieve similar objectives at a fraction of the cost. Supporters argued that SLS and Orion were purpose-built for deep space, with redundancy and safety features that commercial vehicles did not yet have, and that a government-owned rocket ensured continued American leadership in deep space exploration, regardless of the fortunes of any single commercial company. The debate continued for years, but eventually the hardware was built. And on November 16, 2022, SLS flew for the first time. The mission was called Artemis I, and it was uncrewed, a test flight designed to validate the rocket and the Orion capsule before human beings were put aboard. The mission lasted 25.5 days. Orion traveled to the Moon, entered a distant retrograde orbit that carried it farther from Earth than any spacecraft designed for human occupancy had ever gone, and then returned. The total distance traveled was 1.4 million miles, and in most respects, the mission was a success. The rocket performed flawlessly. The spacecraft's navigation, communication, and life support systems worked as designed. The European Service Module, built by Airbus for the European Space Agency, provided propulsion and power without any significant issues. But there was one problem, a serious one. During reentry, the Orion capsule's heat shield behaved in a way that no one had predicted. The heat shield, which protects the crew from temperatures exceeding 5,000 degrees Fahrenheit, as the capsule plunges through the atmosphere at 25,000 miles per hour, experienced unexpected charring and material loss. Pieces of the ablative material, the outer layer designed to absorb and dissipate heat by gradually burning away, separated from the shield in larger chunks than anticipated. The underlying structure was not compromised, and the capsule survived re-entry intact. But the pattern of erosion was not what the engineering models had predicted. Something was happening during the most critical phase of the mission that the engineers did not fully understand. This was deeply concerning. The heat shield is arguably the most critical single component of any spacecraft that returns from deep space. It is the last line of defense between the crew and destruction. At 25,000 miles per hour, the energy of re-entry is so extreme that any significant failure of the heat shield would be catastrophic. There would be no backup, no escape system, no second chance. If the heat shield fails, the crew dies. NASA spent more than 2 years investigating the heat shield anomaly. Teams at the Johnson Space Center, the Kennedy Space Center, and contractor facilities across the country conducted extensive testing, analysis, and modeling. They subjected sample heat shield panels to simulated re-entry conditions in arc jet facilities that recreated the temperatures, pressures, and gas chemistry of atmospheric entry. They developed new computational models to predict how the ablative material would behave under the specific flight conditions of a lunar return trajectory. And they concluded, ultimately, that the heat shield was safe for crewed flight, provided certain conditions were met. The re-entry trajectory was adjusted to reduce the peak heating rate. Additional instrumentation was added to the heat shield for Artemis II, so that engineers could monitor its performance in real time and gather data that would improve future designs. But the investigation delayed Artemis II by more than 2 years. The mission, originally scheduled for late 2024, was pushed first to 2025, then to early 2026. Each delay eroded public confidence and gave critics of the program more ammunition. Some called for the mission to be canceled entirely. Others urged NASA to skip the lunar flyby and proceed directly to a landing mission, arguing that a flyby added risk without significantly advancing the program's scientific objectives. NASA disagreed. A crewed flyby was essential, the agency argued, because Artemis I had been uncrewed. No human being had flown on SLS or inhabited Orion in deep space. The life support systems, the navigation systems, the communication systems, the waste management systems, the radiation monitoring systems, all of these needed to be tested with an actual crew aboard before anyone could be trusted to live in the vehicle for the 2 weeks or more that a landing mission would require. And the heat shield needed to be proven with human lives on the line, not just instrumentation. If there was a problem, it was better to discover it on a flyby mission, where the crew could return to Earth relatively quickly, than on a landing mission, where they might be stranded on the lunar surface with a compromised return vehicle. So the delays continued, the costs mounted, the critics grew louder, and the 4 astronauts chosen for the mission, Wiseman, Glover, Koch, and Hansen, trained. They trained for years. They trained for every conceivable scenario, from nominal operations to cascading system failures. They trained in simulators, in underwater facilities, in aircraft that flew parabolic arcs to simulate weightlessness. They learned every system aboard Orion in intimate detail. They memorized procedures, practiced emergency protocols, and built the kind of deep, intuitive familiarity with their spacecraft that comes only from thousands of hours of repetition. And then, finally, in the early spring of 2026, everything came together. The rocket was ready. The spacecraft was ready. The crew was ready. The weather cooperated, and on the morning of April 1st, the countdown reached 0. Section 3. The Machine. To understand what happened on April 1st, 2026, you need to understand the machine that made it possible. The Space Launch System is not just a rocket. It is, in many ways, the last great monument of the Apollo era's engineering philosophy, adapted and modernized for the 21st century, but built on principles and components that trace their lineage back decades. Understanding SLS is understanding the bridge between the space program that put humans on the moon in the 1960s and the space program that is trying to do it again today. The rocket stands 322 feet tall in its Block 1 configuration, the version used for Artemis I and Artemis II. For comparison, the Saturn V that carried the Apollo astronauts to the moon stood 363 feet tall. SLS is shorter but wider, and it produces slightly more thrust at liftoff. The core stage is the largest single piece of rocket hardware ever manufactured by NASA, measuring 212 feet in length and 27.6 feet in diameter. It is built at the Michoud Assembly Facility in New Orleans, the same facility where the Saturn V's first stage and the Space Shuttle's external tanks were built. It is transported to the Kennedy Space Center by barge, traveling through the Gulf of Mexico and up the coast of Florida, a journey of about 900 miles that takes roughly 2 weeks. The core stage is powered by 4 RS-25 engines, mounted in a cluster at its base. These are the same engines, literally the same physical hardware in some cases, that powered the Space Shuttle. The RS-25 is one of the most thoroughly tested and reliable rocket engines ever built. It was designed in the 1970s by Rocketdyne, first flew in 1981 on the maiden voyage of the Space Shuttle Columbia, and accumulated more than 3,000 test firings and 135 shuttle missions over 30 years of service. For the shuttle, the engines were reusable. They fired during launch, were recovered with the orbiter after each mission, refurbished, and flown again. For SLS, they are expendable. Each set of 4 engines is used once and then lost when the core stage falls into the ocean after separation. This decision was controversial. The RS-25 engines cost roughly $40 to $70 million each. Discarding 4 of them after every flight represents a significant expense. But NASA determined that the cost and complexity of making the core stage reusable would exceed the savings from recovering the engines, at least for the relatively low flight rate planned for SLS. But how does the RS-25 actually work? What happens inside this engine that allows it to produce 512,000 pounds of thrust from 2 of the simplest elements in the universe, hydrogen and oxygen? The answer involves one of the most elegant and demanding engineering cycles ever devised for a rocket engine, the staged combustion cycle. In a staged combustion engine, the propellants, liquid hydrogen and liquid oxygen, are not simply mixed and ignited in the main combustion chamber. Instead, nearly all of the fuel is first routed through a preburner, a small combustion chamber where it is mixed with a portion of the oxidizer and ignited. This preburner produces extremely hot, high-pressure gas that drives the engine's turbopumps, the spinning machinery that forces propellant into the combustion chamber at the enormous pressures and flow rates required for full thrust. The exhaust from the preburner, still rich in unburned hydrogen, is then routed into the main combustion chamber, where it mixes with the remaining liquid oxygen and burns completely. The turbopumps themselves are marvels of engineering. The RS-25's high-pressure fuel turbopump spins at roughly 36,000 revolutions per minute, driven by gas at temperatures exceeding 1,000 degrees Fahrenheit, and it pumps liquid hydrogen at a rate of approximately 70 gallons per second at pressures exceeding 6,000 pounds per square inch. The high-pressure oxidizer turbopump handles the liquid oxygen, spinning at roughly 29,000 revolutions per minute. Together, these pumps deliver propellant to the main combustion chamber at a combined flow rate of roughly 1,000 pounds per second. The power output of each turbopump is equivalent to roughly 70,000 horsepower, which means each RS-25 engine contains turbomachinery producing more power than a nuclear submarine. And there are 4 of these engines on the core stage. The staged combustion cycle makes the RS-25 extraordinarily efficient. It achieves a specific impulse, a measure of how effectively a rocket engine converts propellant into thrust, of 452 seconds in vacuum, among the highest of any chemical rocket engine ever flown. It also makes the engine throttleable, meaning the thrust can be adjusted during flight, a capability that is essential for controlling the acceleration on the crew as the rocket burns through its propellant and grows lighter. The RS-25 can throttle between 67% and 111% of its rated power level, and each engine can be gimbaled or tilted to steer the rocket during ascent. Each RS-25 produces roughly 512,000 pounds of thrust at sea level, using liquid hydrogen as fuel and liquid oxygen as oxidizer. The 4 engines together produce about 2 million pounds of thrust. But that is not nearly enough to lift the fully loaded rocket, which weighs about 6 million pounds on the launch pad. The additional thrust comes from 2 solid rocket boosters, one attached to each side of the core stage. These boosters are derived from the Space Shuttle's solid rocket boosters, but are significantly larger. Each Artemis booster contains 5 segments of solid propellant compared to 4 segments for the shuttle version, and each produces approximately 3.6 million pounds of thrust. Together, the 2 boosters produce about 7.2 million pounds of thrust, accounting for the vast majority of the rocket's total liftoff thrust of 8.8 million pounds. The solid rocket boosters burn for about 2 minutes after liftoff, consuming their entire propellant load in that time. They then separate from the core stage and fall into the Atlantic Ocean. Unlike the shuttle's boosters, which were recovered by ships, refurbished, and reused, the Artemis boosters are not recovered. They sink to the ocean floor. This, again, was a cost-saving measure in terms of operations, trading the expense of recovery and refurbishment for the simplicity of expendability. After booster separation, the core stage continues to fire its 4 RS-25 engines for another 6 minutes, accelerating the upper stage and the Orion spacecraft to a speed of roughly 17,000 miles per hour, fast enough to reach low Earth orbit. The core stage then separates and falls back toward the ocean, breaking apart and sinking in a remote area of the Pacific. Above the core stage sits the Interim Cryogenic Propulsion Stage, or ICPS, a relatively small upper stage powered by a single RHEL-10 engine. The ICPS is built by United Launch Alliance and is derived from the Delta Cryogenic Second Stage used on the Delta IV rocket. Its job is to perform the trans-lunar injection burn. the critical engine firing that accelerates the Orion spacecraft from its parking orbit around Earth to the velocity needed to reach the Moon. This requires increasing the spacecraft's speed by roughly 6,000 miles per hour, a burn that lasts about 18 minutes. After the burn, the ICP-ACE separates from Orion and drifts away, eventually entering a heliocentric orbit around the Sun where it will remain, a small piece of human-made debris circling our star indefinitely. And then there is Orion itself. The Orion multi-purpose crew vehicle is built by Lockheed Martin at their facility in Denver, Colorado. It consists of two main components, the crew module and the European service module. The crew module is the cone-shaped capsule where the astronauts live and work. It is 16.5 feet in diameter, slightly larger than the Apollo command module, which was 12 feet 10 inches in diameter. The additional space is significant. Apollo's command module was famously cramped, with 3 astronauts sharing a habitable volume of roughly 210 cubic feet, about the interior space of a large SUV. Orion's crew module provides about 316 cubic feet of habitable space for 4 astronauts, roughly 50% more volume per person than Apollo. This matters enormously on a mission lasting 10 days or more in deep space, where there's no way to step outside for fresh air. The crew module is covered by a heat shield on its base, the largest heat shield ever built for a crewed spacecraft, measuring 16.5 feet in diameter. It is made of a material called AV coat, an ablative compound that absorbs heat by gradually charring and eroding during re-entry. AV coat has a long history in American spaceflight. It was originally developed in the 1960s and was used on the Apollo command module's heat shield, the very shield that brought the Apollo astronauts safely home from the Moon. For Orion, the manufacturing process was updated and refined, but the fundamental chemistry remains similar. AV coat is a fiberglass honeycomb structure filled with an epoxy-based ablative material. The honeycomb is made up of thousands of individual cells, each about 1.5 inches across, and each cell is filled by hand with the ablative compound using a specialized caulking gun. The entire heat shield contains roughly 320,000 cells, and filling them is a painstaking process that takes months. Once filled, the shield is cured, machined to precise tolerances, and then bonded to the titanium and composite structure of the crew module's base. During re-entry, the outer surface of the AV coat chars and ablates, meaning it transforms into gas and carries heat away from the spacecraft in the outgoing flow. The process is controlled and predictable under normal circumstances, which is precisely why the unexpected behavior during Artemis I was so alarming. The heat shield must withstand temperatures exceeding 5,000 degrees Fahrenheit and dynamic pressures of hundreds of pounds per square foot as the capsule decelerates from 25,000 miles per hour to a few hundred miles per hour in a matter of minutes. This is the component that caused concern after Artemis I, and it is the component that received the most intensive scrutiny before Artemis II was cleared for flight. Orion also carries significant radiation protection features, a critical concern for any spacecraft venturing beyond low Earth orbit. On the International Space Station, the crew is still largely protected by Earth's magnetosphere, the magnetic field that deflects the most dangerous charged particles from the Sun and from deep space. Beyond low Earth orbit, that protection disappears. The crew of Orion would be exposed to 2 primary types of space radiation: solar particle events, which are intense bursts of energetic protons emitted during solar flares and coronal mass ejections, and galactic cosmic rays, which are extremely high-energy particles originating from supernovae and other violent events elsewhere in the galaxy. Galactic cosmic rays are particularly insidious because they are so energetic that no practical amount of spacecraft shielding can fully block them. Orion addresses this threat through a combination of passive shielding, strategic placement of equipment, and water storage to provide additional mass between the crew and the radiation, and an emergency protocol in which the crew can build a makeshift shelter in the center of the capsule using storage bags and equipment, creating a denser barrier around themselves during a solar particle event. The vehicle's radiation monitoring system continuously tracks the crew's exposure and provides real-time alerts if radiation levels spike, giving the crew time to implement protective measures. The navigation system aboard Orion represents another significant advancement over Apollo. The Apollo guidance computer, while revolutionary for its time, had roughly 64 kilobytes of memory and operated at less than 1 megahertz. Orion's avionics system uses multiple redundant flight computers, high-speed data buses, and glass cockpit displays similar to those found in modern commercial aircraft. But the navigation challenge for a deep space mission is fundamentally different from navigating in low Earth orbit. In Earth orbit, the spacecraft can rely on GPS, the constellation of navigation satellites that provides precise positioning anywhere near the planet. Beyond the GPS constellation, roughly 12,000 miles from Earth, Orion must rely on other methods. The spacecraft carries star trackers, precision optical instruments that identify stars in the background sky and calculate the spacecraft's orientation based on their positions. It carries inertial measurement units that track acceleration and rotation, maintaining a running estimate of the spacecraft's position and velocity. And it carries a capability called optical navigation, in which the onboard cameras photograph the Earth, Moon, or Sun against the background stars, and software algorithms calculate the spacecraft's position from the apparent size and location of these bodies in the image. This optical navigation capability provides a backup that is entirely independent of ground-based tracking, meaning the crew could find their way home even if they lost all communication with Earth. The communication system uses NASA's Deep Space Network, a worldwide array of large antenna dishes that maintain contact with spacecraft throughout the solar system. During most of the mission, Orion is in continuous communication with Mission Control in Houston. The only exception is the period when the spacecraft passes behind the Moon, where the Moon's bulk blocks all radio signals between the spacecraft and Earth. Attached to the base of the crew module is the European Service Module, built by Airbus Defence and Space for the European Space Agency. The service module is a cylindrical structure about 16 feet in diameter and 13 feet long. It provides Orion with its primary propulsion system, a single orbital maneuvering system engine adapted from the Space Shuttle, which produces 6,000 pounds of thrust. It also carries 8 auxiliary thrusters and 24 smaller reaction control thrusters for attitude adjustments and minor course corrections. The service module contains 4 solar array wings, each about 23 feet long, which unfold after launch and provide all of Orion's electrical power. Each wing carries 3 panels of high-efficiency gallium arsenide solar cells, a technology originally developed for telecommunications satellites that collectively generate approximately 11 kilowatts of electrical power, enough to run all of Orion's systems including life support, avionics, communications, and thermal control. The solar arrays are designed to track the sun automatically, rotating on their mountings to maintain optimal orientation as the spacecraft changes its attitude during the mission. They are also designed to withstand the thermal extremes of deep space, where temperatures can swing from several hundred degrees in direct sunlight to hundreds of degrees below zero in shadow. The service module also manages Orion's water supply, a critical system for a crew of 4 on a mission lasting more than a week. It carries approximately 240 kilograms of potable water in bladder tanks, and the life support system includes a humidity recovery system that extracts water vapor from the cabin air and recycles it. The water serves multiple purposes: drinking, food preparation, and cooling for the spacecraft's electronics and life support equipment through a network of fluid loops that circulate water through heat exchangers. The thermal control system is essential because in space there is no convective cooling. Heat can only be radiated away into the vacuum, and the spacecraft must carefully balance the heat generated by its electronics and crew against the heat lost through radiation, maintaining a comfortable cabin temperature despite the extreme thermal environment outside. One important difference between Orion and Apollo is the launch abort system. Mounted on top of the crew module during launch is a tower containing a set of solid rocket motors, designed to pull the capsule away from the rocket in the event of a catastrophic failure during ascent. Apollo had a similar system. But Orion's launch abort system is more powerful and more capable, designed to function at any point from the launch pad to an altitude of about 300,000 feet. It can accelerate the crew module from 0 to over 400 miles per hour in less than 3 seconds, pulling it away from an exploding rocket with enough force to press the astronauts into their seats at roughly 7 times the force of gravity. If everything goes well, the launch abort system is jettisoned about 6 minutes after launch. Once the spacecraft is high enough and moving fast enough that the abort motors are no longer needed, it falls away and tumbles back into the ocean, unused. But its presence on top of the rocket during those critical first minutes of flight provides a level of crew safety that was never available on the space shuttle, which had no escape system during ascent. The total mass of the Orion spacecraft, fully loaded with crew, consumables, and propellant, is roughly 57,000 pounds. It is designed to support a crew of 4 for missions lasting up to 21 days, though the typical mission duration is expected to be 10 to 14 days for the early Artemis flights. The crew's living space includes 4 seats for launch and reentry, storage for food and personal items, a small galley area, a waste management compartment, and multiple windows that provide views of the Moon, the Earth, and the surrounding space. That period of communications blackout, lasting roughly 40 minutes on Artemis II, would prove to be one of the most psychologically intense moments of the entire mission. But before we get to that moment, let us follow the crew from the launch pad into space. Because the experience of riding the most powerful rocket ever built by NASA, the sensation of 8.8 million pounds of thrust, pressing you into your seat and hurling you toward the sky at an acceleration that doubles and triples as the propellant burns away and the rocket grows lighter, is something that deserves to be described slowly and carefully. Section 4. The launch and the journey on the morning of April 1st, 2026. The crew of Artemis II woke before dawn. They had slept in the crew quarters at the Kennedy Space Center, the same building where Apollo and shuttle crews had spent their final nights before launch. The building is deliberately isolated, quiet, and secure, designed to give the astronauts privacy and rest in the hours before a mission. Sleep, for most crews on the night before launch, is difficult. The combination of excitement, anticipation, and the simple awareness that tomorrow you will be strapped to several million pounds of explosive propellant tends to keep the mind active. The crew ate breakfast together. They suited up. Each of them helped into their orange advanced crew escape suits by a team of technicians who checked every seal, every connection, every pressure valve with meticulous care. The suits are designed to protect the astronauts in the event of a depressurization during launch or re-entry. They provide a self-contained atmosphere, thermal protection, and enough consumables to sustain the crew for several hours if the cabin environment is lost. The suits are bulky and uncomfortable, but they are not optional. They are the last layer of protection between the crew and the vacuum of space. The crew then walked out of the building, waving to the small crowd of family members and support staff gathered outside, and climbed into the Astrovan II, a modified Airstream trailer that transported them to the launch pad. The drive takes about 20 minutes. Along the way, the road passes through the marshlands and scrubland of the Kennedy Space Center, a nature preserve that hosts alligators, bald eagles, and a surprising variety of wildlife that has adapted to life alongside one of the most technologically intense facilities on Earth. Through the windows, the crew could see the rocket in the distance, standing on the pad, venting streams of white vapor from its cryogenic propellant tanks, lit by xenon spotlights against the pre-dawn sky. At the pad, the crew rode an elevator to the top of the mobile launcher, a massive steel structure that supports the rocket during assembly and provides access to the spacecraft at the top. They walked across the crew access arm, a retractable bridge that extends from the mobile launcher to the hatch of the Orion capsule. One by one, they climbed through the hatch and settled into their seats, lying on their backs with their feet pointed toward the sky. The spacecraft was oriented nose up, so from the crew's perspective, they were looking straight up at the escape tower above them. Through the small windows, they could see nothing but sky. The hatch was closed and sealed, the access arm retracted. The launch team at the Kennedy Space Center's firing room began the final countdown. Systems were checked and rechecked. Propellant pressures were verified. Weather conditions were confirmed. Range safety was established. At 9 minutes before launch, the countdown sequence went automatic, controlled by the ground launch sequencer, a computer system that manages the precise timing of hundreds of events in the final minutes before liftoff. At 6 minutes and 30 seconds before launch, the ICPS upper stage pressurized its propellant tanks. At 5 minutes, the solid rocket booster's safe and arm devices were activated. At 3 minutes and 30 seconds, the Orion spacecraft switched to internal power. At 50 seconds, the core stage's main propulsion system was pressurized to flight levels. At 33 seconds, the ground launch sequencer handed control to the onboard flight computers. At 6 seconds before liftoff, the 4 RS-25 engines ignited in a carefully timed sequence, one after another, at intervals of 120 milliseconds. The engines took about 4 seconds to reach full thrust, during which time the rocket remained bolted to the launch pad by massive hold-down posts. This hold-down period allowed the onboard computers to verify that all 4 engines were operating normally before committing to flight. If any engine had failed to reach full thrust or had shown anomalous readings, the computers could have shut down all 4 engines and aborted the launch while the rocket was still safely on the ground. All 4 engines reached full thrust. The computers confirmed nominal performance across all parameters. At T-0, the two solid rocket boosters ignited, the hold-down posts released, and the most powerful rocket NASA had ever flown lifted off the pad. The sensation of a rocket launch, as described by astronauts who have experienced it, is unlike anything else in human experience. The initial moments are almost gentle. The rocket rises slowly, so slowly that from a distance it seems to hover above the pad, barely clearing the tower. The 8.8 million pounds of thrust are only slightly more than the 6 million pounds of the fully loaded rocket, so the initial acceleration is modest, about 1.3 times the force of gravity. You feel pressed into your seat, but not uncomfortably. But what does the crew actually hear and see in those first seconds? The sound reaches them slightly before the motion, a deep bass rumble that rises from below and penetrates the hull of the capsule, despite all the acoustic insulation surrounding them. It is not a clean sound. It is layered, complex, textured. The four liquid engines produce a steady, high-pitched roar that underlies everything. The two solid rocket boosters add a rougher, grainier sound, a crackling thunder that dominates. The combined noise inside the cabin has been measured at roughly 140 decibels at liftoff, equivalent to standing next to a jet engine, though the acoustic insulation brings it down significantly by the time it reaches the crew's ears through their helmets. Despite the helmet padding and the active noise reduction in the communication system, the sound is pervasive. It does not come from any single direction. It comes from everywhere, transmitted through the structure of the rocket itself, through the seats, through the floor, through the very air inside the cabin. It is felt as much as heard. Through the small windows, the crew can see very little during the first minutes of flight. The capsule is at the very top of the rocket, above the escape tower fairing, and the windows face outward rather than downward. What they see is sky. Blue at first, then darkening as the rocket climbs through the atmosphere. If the sun is in view, it is painfully bright against the deepening indigo. Wispy clouds streak past in an instant. Then the clouds are gone, and the sky turns a deeper and deeper shade of blue, then violet, then black, as the atmosphere thins and falls away below. Within 2 minutes, the crew can see stars, even in the direction of the sun, because the atmosphere that normally scatters sunlight and washes them out is now far below. The transition from bright daytime sky to the blackness of space is surprisingly rapid, and is one of the visual landmarks that astronauts remember most vividly. Then it builds. As the solid rocket boosters burn through their propellant, the rocket grows lighter, but the thrust remains constant. The acceleration increases. The vehicle begins to move faster. The sky outside the windows darkens from blue to indigo to black. The vibration from the solid boosters is intense, a deep, shuddering rumble that travels through the structure of the rocket and into the seats and the bodies of the crew. It has been compared to driving a truck at high speed over a dirt road, or to riding in a small boat through heavy seas. The sound is overwhelming, a sustained roar that penetrates the insulation of the capsule and fills the cabin with a physical wall of noise. At about 2 minutes after liftoff, the solid rocket boosters burned out and separated. This moment was dramatic. Small explosive charges severed the connections between the boosters and the core stage. Separation motors fired, pushing the empty booster casings away from the rocket. From inside the capsule, the crew felt a sudden jolt as the boosters departed, followed by an immediate and striking change in the ride quality. The shuddering vibration of the solid rockets was replaced by the smooth, steady push of the liquid-fueled RS-25 engines. Astronauts who have flown on both solid and liquid rockets describe the difference as going from riding a mechanical bull to floating on a river. The ride becomes quiet, smooth, and progressively more powerful. With the boosters gone, the core stage was still burning, driving the rocket faster and faster. The acceleration continued to build as propellant was consumed, and the vehicle grew lighter. By the time the core stage engines shut down, about 8 minutes after liftoff, the crew was experiencing roughly 3 times the force of gravity. 3 Gs means that your body feels 3 times heavier than normal. A 200-pound astronaut would feel as though they weighed 600 pounds. Breathing becomes effortful. Moving your arms requires deliberate concentration. The blood in your body tries to pool in your legs and feet, away from your head. The pressure suits help counteract this by applying external pressure to the lower body, but the sensation is still distinctly uncomfortable. Then, abruptly, the engines stopped. The core stage separated, and the crew experienced weightlessness for the first time. The transition from 3 Gs to 0 Gs is startling. One moment you are pressed heavily into your seat. The next moment you are floating. Loose items that were held down by the acceleration suddenly drift free. Anything not secured floats up and away. Your arms rise in front of you unless you consciously hold them down. Your internal organs, accustomed to the constant pull of gravity, shift and settle into new positions. Many astronauts experience a sensation of fullness in their head as fluids redistribute in the absence of gravity, a feeling similar to hanging upside down. For the next 2 hours, the crew orbited the Earth aboard the ICPS upper stage, checking systems, verifying the health of the spacecraft, and preparing for the most critical maneuver of the mission, the trans-lunar injection burn. This was the engine firing that would accelerate Orion from its circular Earth orbit at about 17,500 miles per hour to the velocity needed to reach the Moon, about 24,500 miles per hour. The burn lasted approximately 18 minutes, during which the RL-10 engine on the ICPS added roughly 6,000 miles per hour to the spacecraft's velocity. When the burn was complete, the ICPS separated and drifted away. Orion was on its own, coasting on a trajectory that would carry it to the Moon over the next 4 days. Behind the spacecraft, the Earth began to shrink. The crew could see their home planet through the windows, initially filling most of the view, then gradually diminishing in size as the hours passed. Over the course of the first day, the Earth went from a vast blue wall filling the window to a sphere the size of a basketball held at arm's length. By the second day, it was the size of a tennis ball. By the third day, it was the size of a marble. And by the time Orion approached the Moon on the 4th day, the Earth was a small blue dot hanging in the blackness, almost indistinguishable from the brighter stars. This experience, known to the Apollo astronauts as the overview effect, has been described by nearly every person who has seen the Earth from deep space as one of the most profound and transformative moments of their lives. Seeing the Earth as a single, small, fragile sphere, without borders, without nations, without any visible evidence of the billions of people living on its surface, changes something in the observer. Astronauts have spoken of a sudden, visceral understanding of the planet's vulnerability, a sense that all of humanity's conflicts and divisions are rendered meaningless by the sheer scale of the cosmos. The Earth is not the center of anything. It is a tiny island of life in an ocean of emptiness so vast that the human mind cannot truly comprehend it. During the 4-day transit to the moon, daily life aboard Orion settled into a quiet rhythm. The crew divided their time between mission tasks and the mundane necessities of living in a small capsule in microgravity. Meals were prepared in the small galley area, where food was stored in labeled pouches and containers. Most of the food was thermostabilized, meaning it had been processed with heat to prevent spoilage and could be eaten at room temperature, or warmed using a small food heater. Some items were freeze-dried and needed to be rehydrated with hot water before eating. The crew ate with utensils that had small magnets in their handles, designed to stick to the metal trays and prevent them from floating away mid-bite. Crumbs were a constant concern, because in microgravity, a stray crumb of bread does not fall to the floor. It floats through the cabin, potentially drifting into equipment, air vents, or someone's eye. For this reason, tortillas were preferred over bread, a tradition that began on the space shuttle and continued to the International Space Station. Sleep in microgravity is a peculiar experience. Without gravity, there is no natural sensation of lying down. The crew used lightweight sleeping bags tethered to the walls of the capsule, zipping themselves in so they would not float around the cabin during the night and bump into equipment or each other. Eye masks and earplugs were essential, because in a capsule the size of a small room, shared by 4 people, there is always some ambient light from instrument panels and some noise from the life support fans. The circadian rhythm, the body's internal clock, tends to drift in space, where there is no natural sunrise or sunset. Mission planners carefully scheduled the crew's sleep and wake cycles to maintain a consistent rhythm, with artificial lighting that shifted from brighter, bluer tones during the work period to dimmer, warmer tones before the scheduled sleep period. Hygiene was managed with wet wipes and no-rinse body wash, as there is no shower aboard Orion. Water is too precious and too difficult to manage in microgravity to use for bathing. The crew brushed their teeth with edible toothpaste that could be swallowed rather than spit out, to avoid the problem of managing floating blobs of toothpaste and water in the cabin air. The waste management system, a topic that astronauts universally describe as the least glamorous aspect of spaceflight, was a small compartment with a fan-assisted system that used airflow to direct waste into containment bags in the absence of gravity's helpful downward pull. As Orion traveled farther from Earth, the crew passed through one of the most hazardous regions of near-Earth space, the Van Allen radiation belts. These are zones of intense radiation trapped by Earth's magnetic field, forming 2 concentric donut-shaped regions around the planet. The inner belt, centered at an altitude of roughly 2,000 miles, is composed primarily of high-energy protons. The outer belt, centered at roughly 12,000 miles, contains mostly high-energy electrons. Passing through these belts exposes the crew to elevated radiation levels, though the transit is relatively brief, lasting only about an hour for each belt, and the Orion spacecraft's shielding limits the absorbed dose to levels well within safety limits. Beyond the Van Allen belts, the radiation environment changes character but does not disappear. The crew was now exposed to galactic cosmic rays, the high-energy particles that originate from outside our solar system. These particles, mostly protons and heavier atomic nuclei, travel at nearly the speed of light and carry so much energy that they can penetrate through the walls of the spacecraft and into the crew's bodies. Each cosmic ray that passes through human tissue has the potential to damage DNA, potentially contributing to an increased cancer risk over a lifetime. The total radiation dose for the Artemis II crew over the 10-day mission was carefully monitored and remained within the limits set by NASA's radiation health standards. But it was significantly higher than what the same crew members had experienced during their previous missions on the International Space Station, which orbits within the protective envelope of Earth's magnetic field. The crew's bodies began changing almost immediately upon reaching weightlessness. Without gravity constantly pulling fluids downward, blood and other body fluids shifted toward the head and upper body, causing faces to appear puffy and swollen while legs became thinner, a phenomenon astronauts call bird legs. The heart, no longer needing to pump against gravity to supply blood to the brain, began to reduce its workload, and over the course of the mission would lose a small but measurable amount of cardiac muscle mass. The bones, no longer bearing the weight of the body, began to slowly lose calcium, a process that would become a serious concern on longer missions, but was negligible over 10 days. The crew performed prescribed exercise routines using resistance bands and isometric exercises to maintain muscle tone and cardiovascular health, though the limited space inside Orion made vigorous exercise difficult. Communication with families was possible through the Deep Space Network, though the increasing distance introduced a growing time delay. Near Earth, the delay was negligible. By the time Orion was halfway to the Moon, the round-trip signal delay was roughly 2.5 seconds. This does not sound like much, but it is enough to make a natural conversation feel slightly stilted, with awkward pauses as each person waits for their words to reach the other. The crew could also send and receive email, text messages, and pre-recorded video messages, which became the preferred method of personal communication as the distance grew and the delay lengthened. And they tested the communication links with mission control, verifying that the Deep Space Network could maintain reliable contact at increasing distances. They tested the life support system, monitoring the cabin atmosphere for proper levels of oxygen, nitrogen, carbon dioxide, temperature, and humidity. They tested the water recovery system, which recycled humidity from the cabin air and processed wastewater to reduce the amount of fresh water the spacecraft needed to carry. They tested the radiation monitoring system, which tracked the crew's exposure to galactic cosmic rays and solar energetic particles, the invisible but potentially dangerous radiation that permeates deep space beyond the protection of Earth's magnetic field. And they ate, slept, exercised, and lived in their small capsule, figuring out the rhythms and routines of daily life in a space smaller than most studio apartments, in a vehicle traveling through the emptiness between worlds at thousands of miles per hour, with nothing but the thin aluminum walls of the spacecraft separating them from the lethal vacuum outside. On the 4th day, the moon grew large in the windows. Section 5. The Far Side. The moon, seen from a distance of a few hundred miles, is breathtaking and alien. It fills the window. Its surface is a landscape of craters, mountains, and vast dark plains that the early astronomers called Maria, the Latin word for seas, because through their primitive telescopes, these smooth, dark regions looked like bodies of water. They are not water. They are ancient lava flows, billions of years old, that flooded enormous impact basins in the moon's crust and solidified into the dark basaltic rock that gives the lunar near side its distinctive face. But how did the moon itself come to be? The leading scientific theory, supported by decades of evidence including the very lunar samples that Apollo brought home, is called the giant impact hypothesis. roughly 4.5 billion years ago, when the Earth was still young, still molten, still forming, a body roughly the size of Mars collided with it. This impactor, sometimes called Theia, struck the Earth at an oblique angle and at a velocity of roughly 25,000 miles per hour. The collision was so violent that it partially melted both bodies, vaporizing enormous quantities of rock and metal, and hurling a vast cloud of debris into orbit around the battered Earth. Over the course of a few thousand years, a geological eye blink, this orbiting debris coalesced under its own gravity and formed the Moon. This origin explains several puzzling features of the Earth-Moon system. Why the Moon has such a relatively large size compared to Earth. Why its composition is similar to Earth's mantle but depleted in iron. And why the Moon's orbit is tilted relative to the plane of the solar system. The Moon is not a captured wanderer. It is a piece of Earth itself, torn free in a cataclysm so immense that it reshaped the entire inner solar system. The far side of the Moon looks completely different from the near side. While the near side is marked by large, dark maria that give it the familiar pattern we see from Earth, the far side is almost entirely covered by bright, heavily cratered highlands. There are few maria on the far side. The crust is thicker there, for reasons that are still not fully understood, and the ancient impacts that created the Great Basins were less likely to produce lava flooding. The result is a landscape that looks older, rougher, more battered. Every crater is surrounded by the rims and ejecta of other craters. The surface is a palimpsest of impacts layered upon impacts layered upon impacts, a geological record of 4.5 billion years of bombardment written in stone. The most dramatic feature on the far side is the South Pole Aitken Basin, one of the largest known impact structures in the entire solar system. It stretches roughly 1,500 miles across and reaches depths of more than 5 miles below the surrounding terrain. It was created by an asteroid impact billions of years ago, an impact so powerful that it may have punched through the Moon's crust entirely and excavated material from the upper mantle. The basin is so old that subsequent impacts have cratered its floor extensively, and its original features have been softened by billions of years of smaller impacts. But its sheer size is still visible from orbit, a vast depression in the lunar far side that dwarfs every other feature on the Moon. Scientists believe that studying the rocks within the South Pole Aitken Basin could reveal the composition of the Moon's deep interior, providing clues about the original giant impact that formed the Moon and about the early history of the inner solar system. It is one of the highest priority scientific targets for future lunar exploration, and the crew of Artemis II, passing over it at a distance of just a few hundred miles, had a perspective on it that no previous human observers had enjoyed at such proximity. No human being had seen the far side of the Moon with their own eyes until the crew of Apollo 8 orbited the Moon in December of 1968. Frank Borman, Jim Lovell, and Bill Anders were the first humans to see that hidden landscape, and their descriptions of it were tinged with awe and a certain loneliness. The far side was strange, unfamiliar. There were no landmarks, no recognizable features, nothing that connected to any map or photograph they had studied. It was, in the most literal sense, terra incognita, unknown territory, the backside of a world that humanity had stared at for thousands of years without ever seeing its other face. The Apollo 8 mission is remembered today primarily for the Earthrise photograph and for its Christmas Eve broadcast, one of the most watched television events of its time. On December 24, 1968, as the spacecraft orbited the moon, the three astronauts took turns reading from the book of Genesis, beginning with the words, "In the beginning, God created the heaven and the earth." The broadcast lasted about 5 minutes and was watched by an estimated 1 billion people around the world. It came at the end of 1968, a year scarred by political assassinations, the Vietnam War, and social upheaval, and it provided a moment of shared wonder that transcended the turmoil. The crew of Artemis II, passing over similar terrain nearly 60 years later, carried with them the awareness of that earlier moment. The knowledge that they were retracing a path first opened by three men in a spacecraft far more primitive than their own, in a year when the world desperately needed something to look up at. And there was something else that happened on the far side. Something that every Apollo crew experienced, and that the Artemis II crew would experience as well. The loss of contact with Earth. As Orion swung around the moon's far side, the 239,000 miles of empty space between the moon and the Earth were supplemented by the moon itself, a sphere of rock 2,160 miles in diameter, interposed directly between the spacecraft and any antenna on Earth's surface. Radio waves cannot pass through solid rock. There is no signal relay satellite orbiting the moon. There was no way to communicate. For approximately 40 minutes, the crew of Artemis II was entirely alone. This is a peculiar kind of alone. It is not the aloneness of being in a remote cabin or a boat far from shore. In those situations, you know that other people exist, that they are reachable, that help could come if you needed it. The aloneness of the lunar far side is qualitatively different. You are farther from any other human being than any person in history. You are behind a world. The entire planet you came from, every person you have ever known, every voice you have ever heard, is on the other side of a sphere of rock that is completely opaque to every form of communication humanity has ever devised. If something goes wrong, no one on Earth will know until you emerge from the other side. If something goes catastrophically wrong, no one on Earth will ever know what happened at all. The psychological weight of this isolation is difficult to convey to anyone who has not experienced something analogous. Consider that every human being who has ever lived, with the exception of the 27 people who have traveled to the moon, has existed within a web of connection that, however strained, was never truly severed. Even the most remote explorers, the sailors who crossed unknown oceans, the climbers who summited the highest peaks, remained on the surface of a planet surrounded by an atmosphere that could carry sound, under a sky shared with every other living being. The crew of Artemis II was not on the surface of a planet. They were in a metal box, in a vacuum, behind a dead world, 240,000 miles from the nearest other person, with the sum total of human civilization blocked from view and from contact by 2,000 miles of rock. There is no remoteness on Earth that approximates this condition. The Apollo astronauts described this experience in varied ways. Some found it exhilarating, a sense of ultimate exploration, of being truly at the frontier. Others found it unsettling. Michael Collins, the command module pilot on Apollo 11 who orbited the moon alone while Armstrong and Aldrin walked on the surface, called it not loneliness but awareness, an acute awareness of his situation, of the fragility of the machinery that kept him alive, of the immensity of the darkness outside his window. Collins later wrote that during his solo orbits of the moon, he felt not fear but a heightened sense of being alive, of every system on the spacecraft becoming intensely personal, because each one was directly responsible for his continued existence. For the Artemis II crew, the loss of signal occurred precisely as planned. The flight controllers in Houston watched their screens as the telemetry from Orion grew intermittent, then stuttered, then went silent. A calm voice in mission control announced, "Loss of signal." And for the next 40 minutes, the 4 astronauts were on their own. Inside the capsule, the crew continued to work. They photographed the lunar surface through the windows, documenting features that had been studied by robotic probes but never seen directly by human eyes at this proximity. The cameras aboard Orion were vastly superior to anything Apollo had carried. Digital imaging sensors with resolutions measuring in the tens of megapixels captured the lunar surface in extraordinary detail, revealing textures and color variations invisible to the naked eye. The crew photographed crater walls striated with layers of different geological epochs. They captured the long shadows cast by mountains and ridgelines in the low-angle sunlight. Shadows that revealed subtle topographic features flattened out in orbital photographs taken from directly above. They documented bright rays of ejected material radiating from young impact craters, fresh in geological terms though still millions of years old. And they photographed the terminator, the line between the sunlit and shadowed portions of the surface, where the oblique lighting cast the rugged terrain into sharp, dramatic relief that revealed every ridge, every boulder, every undulation in the ancient surface. They monitored their instruments. They checked their trajectory, verifying that the spacecraft was following the planned free return path that would sling them around the moon and send them back toward Earth without any additional engine burn. This free return trajectory was a deliberate safety feature. If the service module engine failed, if all propulsion was lost, the spacecraft would still return to Earth on its own, carried by the moon's gravity around the far side and flung back toward home on a path that would arrive at Earth's atmosphere at the correct angle for a survivable reentry. They also looked out the windows, and what they saw was something that only 27 people in all of human history have ever seen: an Earthrise. From the surface of the moon, the Earth does not rise or set. Because the moon is tidally locked, always showing the same face to the Earth hangs motionless in the lunar sky, never moving, never setting, always in the same position. But from lunar orbit, the situation is different. As the spacecraft circles the moon, the Earth appears to rise above the lunar horizon, just as the sun appears to rise above Earth's horizon when our planet rotates. The Earth comes into view gradually, a sliver of blue and white emerging from behind the gray, cratered edge of the moon, growing and brightening until the full disk is visible, hanging in the blackness above a desolate landscape. The most famous photograph ever taken, arguably, is the Earthrise photo captured by Bill Anders on Apollo 8 in December of 1968. It shows the Earth, half lit by the sun, rising above the limb of the moon, a vivid sphere of blue and white against the absolute blackness of space. That single image is credited with helping to catalyze the modern environmental movement by showing humanity, for the first time, what their planet looked like from the outside. A fragile, beautiful, isolated world, with no visible boundaries between nations, no evidence of war or conflict, just oceans and clouds and continents glowing in the sunlight. The Artemis II crew saw their own Earthrise, and they photographed it with cameras far superior to anything the Apollo astronauts had carried. The images they captured, released to the public within hours of their return, showed the Earth in extraordinary detail. Cloud patterns over the Pacific, the brown and green of the Amazon basin, the ice cap of Antarctica, the curve of the Terminator, the line between day and night, sweeping across Africa, and all of it framed by the lifeless gray of the lunar horizon, a contrast so stark that it seemed almost staged, as if the universe had arranged the scene to make a point about the difference between life and its absence. But the most striking moment came not during the photography, but during the silence. During the 40 minutes of communications blackout, the crew later reported, there was a period when all 4 of them stopped working simultaneously. They were not following a procedure. No one gave an order. They simply stopped, floated near the windows, and looked out at the moon below and the stars above. The silence inside the capsule was broken only by the quiet hum of the life support fans and the occasional click of an instrument. Outside, the universe was absolutely still. Commander Wiseman later described this moment in a post-mission interview. He said that he had been to space before, on the International Space Station, and had thought he understood what the overview effect felt like. But the ISS orbits at 250 miles. The moon is 1,000 times farther. And the experience of looking at the Earth from that distance, he said, was not a more intense version of the same feeling. It was a completely different feeling. On the ISS, the Earth fills your vision. You are close enough to see cities, highways, the wakes of ships. You feel connected to the surface. From the moon, the Earth is small, startlingly small, and the space between you and it is not empty. It is vast. You realize, in a way that no photograph or description can prepare you for, that you are somewhere else. Not just far from home, but at another world, in a void so large that the word distance does not adequately describe it. And then, as the spacecraft completed its pass around the far side and the lunar horizon began to rotate beneath them, the antenna on Orion reacquired the signal from the Deep Space Network. Telemetry began streaming back to Houston. A voice in Mission Control said, "Acquisition of signal. Artemis II. Houston, we have you back. How do you read?" And Commander Wiseman replied, his voice steady but carrying an unmistakable undercurrent of emotion. "Houston, Artemis II. We read you loud and clear. It is good to hear your voice." The crew had rounded the moon. They had passed through the shadow. They had seen what only a handful of human beings had ever seen. And now they were coming home. Section 6. Coming Home. The return journey from the moon takes approximately 4 days. A long, quiet coast through empty space with the Earth growing slowly larger in the windows. For the crew of Artemis II, these days were filled with continued system checks, debriefings with Mission Control, and the gradual adjustment of their daily routines as they prepared for the most dangerous phase of the mission. Reentry. Reentry from lunar distance is fundamentally different from reentry from low Earth orbit. A spacecraft returning from the International Space Station re-enters the atmosphere at roughly 17,500 miles per hour. A spacecraft returning from the moon re-enters at roughly 25,000 miles per hour. That additional 7,500 miles per hour represents an enormous increase in kinetic energy, because kinetic energy scales with the square of velocity. At 25,000 miles per hour, the kinetic energy is roughly twice what it would be at 17,500 miles per hour. All of that energy must be dissipated during re-entry, converted from kinetic energy into heat through friction with the atmosphere. The temperatures on the heat shield reach over 5,000 degrees Fahrenheit, hot enough to melt steel, hot enough to ionize the air surrounding the capsule, into a sheath of superheated plasma that blocks all radio communication for several minutes. This plasma blackout is another moment of profound isolation, similar in kind to the communications blackout behind the moon, but different in character. Behind the moon, the crew was safe, coasting on a predictable trajectory with plenty of time and resources. During re-entry, the crew is in the most dangerous phase of the entire mission. The heat shield is absorbing thousands of degrees of heat. The capsule is decelerating at forces that push the astronauts deep into their seats. The spacecraft is surrounded by a cocoon of plasma at temperatures rivaling the surface of the sun, and for about 5 minutes, there is no way to communicate with anyone. Mission Control can only watch their screens and wait. For Artemis II, the re-entry was additionally freighted with the memory of the heat shield anomaly from Artemis I. Although NASA had cleared the heat shield for crewed flight, the uncertainty lingered. The engineers were confident. The analysis was thorough. The adjustments to the re-entry trajectory had been made specifically to reduce the peak heating on the heat shield. But until the capsule was safely through the atmosphere and hanging beneath its parachutes, no one could be entirely sure. The re-entry sequence began when the service module was jettisoned. The European service module, which had provided propulsion, power, and consumables for the entire mission, separated from the crew module and was left behind. It would re-enter the atmosphere separately and burn up. Its job complete. The crew module, now, alone, oriented itself with its heat shield facing forward, into the direction of travel. At an altitude of roughly 75 miles, the capsule contacted the upper atmosphere. At first, the deceleration was gentle, a slight vibration, a faint orange glow appearing at the edges of the windows. Then, rapidly, the heating intensified. The glow became a blaze. The capsule was surrounded by fire, the air around it compressed and heated to incandescence. From the outside, the capsule would have looked like a shooting star, a brilliant streak of light cutting across the sky. From the inside, the crew could see nothing but orange and white fire filling the windows. The G-forces built, pressing them into their seats at roughly 4 to 5 times the force of gravity. The capsule shook and buffeted as it plowed through the increasingly dense atmosphere. And then, as quickly as it had begun, the heating subsided. The glow faded. The G-forces decreased. The capsule had slowed to subsonic speed, still miles above the surface but through the worst of the re-entry. The drogue parachutes deployed first, 2 small chutes that stabilized the capsule and slowed it further. Then the 3 main parachutes deployed, enormous canopies of orange and white fabric that blossomed above the capsule and arrested its descent to a gentle 11 miles per hour. The capsule splashed down in the Pacific Ocean on April 11, 2026. Recovery ships from the United States Navy were waiting nearby. Divers leaped into the water and attached a flotation collar to the capsule. The hatch was opened, and one by one, the 4 astronauts emerged, blinking in the sunlight, breathing fresh air for the first time in 10 days, smiling. They had done it. They had gone to the moon and come back. The first humans to leave low Earth orbit in more than half a century. The first crew to fly the Space Launch System. The first humans to inhabit the Orion spacecraft in deep space. The first to test the systems, endure the radiation, survive the re-entry, and prove that the hardware worked. They had validated the Artemis architecture. They had demonstrated that the path to a permanent human presence on the moon was viable. But Artemis II was never meant to be the end. It was always meant to be a beginning. The Artemis program's next mission, Artemis III, is planned to land astronauts on the lunar surface for the first time since Apollo 17. The landing is expected to take place near the lunar South Pole, in the vicinity of the permanently shadowed craters where water ice has been confirmed. The selection of the specific landing site is one of the most carefully considered decisions in the program. Scientists and engineers have identified 13 candidate landing regions, each evaluated on the basis of illumination conditions, terrain slope, communications access, and proximity to permanently shadowed craters that may contain water ice. The ideal site would offer nearly continuous sunlight for solar power generation, a feature unique to the lunar poles where the sun hovers just above the horizon, while also being within a short traverse distance of permanently shadowed areas where ice deposits can be accessed. The rim of Shackleton Crater near the Moon's south pole has been identified as one of the most promising candidates. The rim receives sunlight for roughly 90% of the lunar day, while the crater's interior has not seen sunlight in billions of years, and is among the coldest places in the solar system, with temperatures dropping below minus 370 degrees Fahrenheit, cold enough to trap and preserve water ice indefinitely. The lander for Artemis III will be a modified version of SpaceX's Starship, a massive vehicle standing roughly 160 feet tall in its lunar configuration. Starship is the largest and most powerful rocket ever built, dwarfing even the Saturn V. The lunar variant, called the Human Landing System, would be pre-positioned in a near rectilinear halo orbit around the Moon, refueled by tanker launches from Earth and waiting for the Orion crew to arrive and transfer over. The sheer size of Starship offers advantages that no previous lunar lander could match. It can carry roughly 100 metric tons of cargo to the lunar surface, compared to the few hundred kilograms that Apollo's lunar module could deliver. This capacity would allow it to carry not just 2 astronauts and their life support supplies, but also scientific instruments, experimental equipment, and, potentially, the components for small surface structures. 2 astronauts would descend to the surface using an elevator system, since the crew cabin sits atop the vehicle roughly 50 feet above the ground, and spend several days conducting experiments and collecting samples before ascending back to orbit to rejoin Orion for the trip home. Beyond Artemis III, the plans grow more ambitious. Artemis 4 and 5 will involve longer stays on the surface and the construction of the Gateway Station, a small orbital outpost positioned in a near rectilinear halo orbit around the Moon, an orbit that brings it as close as 2,000 miles to the lunar surface at its nearest point and as far as 43,000 miles at its farthest. This unusual orbit provides several advantages. It requires very little propellant to maintain. It provides convenient access to the lunar surface for landing missions, and it allows nearly continuous communication with Earth. The Gateway will be much smaller than the International Space Station, roughly the volume of a small studio apartment, but it will serve multiple purposes. It will function as a staging point where crews arriving from Earth in Orion can transfer to a lunar lander for descent to the surface. It will serve as a science laboratory for studying the deep space radiation environment, lunar geology, and the long-term effects of living beyond Earth's magnetosphere. And it will act as a test bed for technologies and operations needed for eventual missions to Mars, including long-duration life support, autonomous systems, and deep space communication. The longer-term vision for the Artemis program extends to the construction of permanent surface habitats near the lunar South Pole. These habitats would be pressurized structures, likely composed of rigid modules augmented by inflatable sections, that could support crews for stays of weeks or months rather than the few days planned for the earliest landing missions. A critical enabling technology for permanent habitation is in situ resource utilization, or ISRU, the practice of using local materials to produce consumables rather than transporting everything from Earth. On the Moon, this means extracting water ice from permanently shadowed craters and processing it into drinking water, breathable oxygen, and rocket propellant. ISRU would fundamentally change the economics of lunar exploration. Currently, every kilogram of material used on the Moon must be launched from Earth's surface at a cost of thousands of dollars per kilogram. If water and oxygen can be produced locally, the amount of material that must be shipped from Earth drops dramatically, making sustained operations far more affordable. NASA has already developed and tested prototype ISRU systems on Earth, including small-scale devices that can extract oxygen from simulated lunar regolith by heating it and capturing the released gases. Demonstrating these technologies on the actual lunar surface is one of the highest priorities for the Artemis program. And beyond the Moon lies Mars, the red planet, 140 million miles away at its closest approach, a journey of roughly 7 to 9 months each way, depending on the trajectory chosen, has been the ultimate goal of human spaceflight since the very beginning. The challenges of a crewed Mars mission are staggering and extend far beyond anything required for lunar exploration. The transit time alone dwarfs any previous human spaceflight. The shortest practical trajectory, using a Hohmann transfer orbit, requires roughly 7 months in each direction, with a surface stay of roughly 500 days waiting for the planetary alignment that allows a return trip. The total mission duration, from launch to landing back on Earth, would be roughly 2.5 to 3 years. No human being has ever spent that long in space in a single mission. The current record, held by Russian cosmonaut Valery Polyakov, is 437 days aboard the Mir space station. The radiation exposure for a Mars mission is one of the most serious unsolved challenges. Over the roughly 30 months of the mission, the crew would accumulate a total radiation dose from galactic cosmic rays and potential solar particle events that significantly exceeds the career limits currently set by most space agencies. Galactic cosmic rays cannot be effectively shielded by any practical amount of material, because the high-energy particles actually generate secondary radiation when they collide with shielding material, a phenomenon called spallation, which can, in some cases, make the radiation environment inside the spacecraft worse rather than better. The solution may involve active shielding, using powerful magnetic or electrostatic fields to deflect charged particles, but such technology is still in the early research phase. The crew would need to carry or produce all of their food, water, and oxygen for the entire journey, with no possibility of resupply from Earth. The time delay in communications, up to 22 minutes each way when Mars is at its greatest distance from Earth, means the crew would need to operate independently, making their own decisions without real-time guidance from mission control. A medical emergency that would be routine in a hospital on Earth could be life-threatening on a Mars mission, where the nearest doctor might be the crew's own flight surgeon, working with limited supplies and limited surgical capability, millions of miles from the nearest hospital. And the psychological challenges of spending years in a confined space, millions of miles from home, with no possibility of rescue, are largely unknown and potentially severe. The total isolation, the monotony, the interpersonal friction of living in close quarters with the same small group for years on end, the knowledge that rescue is physically impossible. All of these factors combine to create a psychological environment unlike anything any human being has ever endured. But Artemis represents the first concrete steps toward making that journey possible. Every system tested on Orion, every lesson learned about deep space radiation, every technique developed for living and working beyond Earth orbit brings humanity closer to the day when a crew will board a spacecraft, leave Earth orbit, and set course not for the Moon, but for Mars. The Moon is the proving ground. It is where the technologies, the procedures, the medical protocols, and the human experience of deep space exploration will be refined and validated before anyone attempts the much longer and much more dangerous voyage to another planet. The long-term vision extends further still. Some planners and visionaries speak of a cis-lunar economy, an economic ecosystem in the space between the Earth and the Moon, where commercial activities such as manufacturing, resource extraction, tourism, and energy production become self-sustaining, generating revenue rather than consuming government budgets. The idea of a permanent, economically productive human presence in space, rather than a series of government-funded expeditions, represents a fundamental shift in how humanity relates to the cosmos. Whether that vision will be realized in this century, or whether it remains an aspiration for future generations, depends in no small part on the success of Artemis and the programs that follow it. That day is not tomorrow. It may not be this decade. But it is closer now than it has ever been, because of what happened on April 1st, 2026. Because 4 people climbed aboard a rocket, left the only world that has ever sustained human life, traveled 250,000 miles through the emptiness of space, swung around the far side of the Moon in absolute silence, and came home safely. Eugene Cernan's initials are still in the lunar dust. TDC. They have not been disturbed. No wind has blown them away. No rain has washed them clean. They sit there, exactly as he left them, in a vacuum so perfect that they could remain legible for millions of years. The Moon is patient. It has waited 53 years for someone to come back. It can wait a little longer, but perhaps it will not have to wait much longer at all. And perhaps the next time someone kneels in the lunar dust and traces letters with their finger, they will not be saying goodbye. They will be writing the first word of a story that has no ending. A story of a species that looked up at the night sky, built the machines to reach it, faltered, waited, and then reached again. The Moon is still there, tonight, outside your window. Look for it, if you like, or close your eyes and let it find you. Either way, it is closer now than it has been in a very long time. Not in distance, in intention, in commitment, in the quiet, stubborn belief that the footprints we leave on other worlds are not endings, but beginnings. And with that thought, let yourself drift. The journey is over. The crew is home. The Moon is waiting. And somewhere, in a future that feels just a little more real tonight than it did yesterday, the next chapter is already being written. Good night.